So we're going to be learning about something called U substitution, which is basically anti-chain rule. We've learned how to do anti-power rule, we've learned how to do anti-trig function. Now we're going to learn how to do anti-chain rule. We'll learn how to do anti-product rule as well, but not today. We're going to do U sub for at least 2 days, and then anti-product rule. So if we're going to do anti-chain rule, we should review chain rule to see if we can figure out a pattern of how could we do it backwards. So when we differentiate using chain rule, we had to do derivative of the outside, evaluated at the inside, times the derivative of the inside. So since you guys know how to do chain rule, I want you guys to do this really quick and find the derivative of negative e to the cosine of x. Okay, so you guys all got negative e to the cosine x times negative sine x. And I am not going to combine those negatives. We'll see why in a second. So if that is the derivative, and we want to anti-differentiate, if we integrate negative e to the cosine x times negative sine x dx, what should the integral of this be? Going backwards.
Should it just be negative e to the cosine?
Should just be negative e to the cosine x. We take our answer and go back to what we were originally working with if we're anti-differentiating. So, negative e to the cosine x. We do need one more thing because it's an indefinite integral. We always have to put when we integrate if there are no bounds. Plus c. We haven't been seeing that as much lately. We haven't been seeing C very much lately. Okay, so if I integrate this, what went away when we integrated? Negative sine x. And the dx always goes away, but just it did disappear. All we were left with was negative e cosine x. So this was the derivative of the inside, right? Derivative. Or in other words, u prime. U prime disappeared. The derivative of the inside disappeared when we did the anti-derivative. So we need to be able to figure out what is u prime and make it disappear just like it did here when we go through a problem that we don't know the answer to. I already asked that question. We don't need to write it down. So we are dealing with a much more complicated integral than we've seen before. Almost always we've been dealing with polynomials or something we could rewrite to look like a polynomial, or trig functions where we just had to have them memorized. We have x squared times square root of 5 plus 2x cubed dx. So we still need to be able to identify the inside of the function, just like we did when we were doing chain rule. We need to be able to identify what's the inside of the function. This time we're going to have a lot of extra stuff too that's neither the inside or the outside. He's always very loud when he shows his videos. Right, so looking at this function, what would the inside be? What's kind of inside something else? 5 plus 2x to the third. That one is inside the square root. Functions that we can usually have inside stuff are like trig functions, sine of something, stuff inside the sine function. Exponential functions, e to the something, we can have e to the 2x plus 5, that's inside the function e. If we're ever raising to a higher power, like to the fifth, so 5x plus 2 all to the fifth, we would consider the 5x plus 2 to the inside. Those we could technically multiply out, but do we really want to multiply something to the fifth out when it's a binomial? It would take a very, very long time. So we identify the inside, and then we find du dx. And I write this specifically as du dx for a reason. We do not want to write it as u prime, because we're going to actually solve for dx. We're going to solve individually for this piece so that we can do some replacing. This is why it's called U substitution. We're going to do a lot of substituting of stuff. So we take the derivative. That part's easy. It's just power rule. So what's our derivative? 6x squared minus 1. And then we want to solve for dx. So did you guys have Miss McDonald? Yes. Do you remember switchy witchy? Yes. Yeah. She called it switchy witchy. The shortcut is just you can switch this right side with the dx on the bottom. We still can do it the long way. We can multiply by dx on both sides. And then divide by 6x squared. But in the end, it really just switches where the dx is and where the 6x squared is. So dx is du over 6x squared. So if you want to remember it by switchy witchy, you can. If you want to just solve using algebra, you can. Either way works. Yes, it is. So we can now substitute. We now know something for dx. And we also said u equals 5 plus 2x to the third. So we know something that 5 plus 2x to the third equals. So I can substitute. Notice x squared, it didn't have anything it was relating to, so we leave it how it is. So we have the integral of x squared times the square root of u, because we said u is equal to 5 plus 2x to the third, times, instead of dx, we're going to replace dx with du over 6x squared. Now we face a problem because I cannot integrate if I have an x and a u in the same sentence, unless we've moved on to multivariate calculus, which we have not. But you should be able to see a pretty easy solution to this.
Can we separate them?
Nope.
No.
But what could we maybe simplify so that we only have the x squared can cancel out with the x squared underneath du. So if a problem is going to work by substitution, almost all the time those cancel out right away. There are some harder versions where you have to do a few more steps to make it work out. We're not doing those today. So it should always cancel out, and now we only have u's left. So I really have the integral of 1 over 6. I'm going to rewrite this as u to the 1/2 du. The whole purpose of that whole process was to get it to something I could integrate. Do we know how to integrate u to the 1/2?
Yes.
We do. It's just a power rule problem. or anti-power rule problem. So now we anti-differentiate. I add 1. 1/2 plus 1 is 3/2. And then I divide by 3/2, which is the same. So we'll find by 2/3. So we have 1/6 times 2/3. Now this is an indefinite integral, so I do need to write plus c. And then I can reduce my fraction. We really have 1/9. Okay, but the problem is my original question was with x's, and now my answer has a u, which is not acceptable. We started with x's, we should end with x's in this process. But we know what u equals. What did u equal? 5 plus 2x to the third. So we get 1/9. 5 plus 2x to the third to the 3/2 plus c. I don't think I like the way I wrote this. Substitute back into u is probably enough. Okay, so I'm going to have you guys try a problem. The integral of cosecant squared of 7x dx. Okay, so all of you guys got -1/7 cotangent 7x plus c. Now this time when we did our u sub, we didn't have any x's cancel out, but if we hadn't done the u substitution, we would have not gotten this 1/7. So even though none of the x's canceled out, it usually comes up with this extra factor, because this is the opposite of the derivative of the inside. If we took the derivative of the inside 7, we'd have to multiply by this, which would get us back to 1 in front. So, with trig functions, we can also have some trickier setups where it's a little bit harder to decide what's the inside that we are working with. We don't even really need to identify the outside. We really just need to identify the inside when we're doing u substitution. So we have sine cubed x cosine x dx. The tricky part here isn't doing the u substitution itself, it's just identifying what are we using for u. What's going to be our best option for u. So when we have trig functions that have those exponents, I usually try and think of them as parentheses sine x to the third cosine x dx. Because now it's a little bit easier to see what's the inside. So what do we think the inside is now that we've rewritten it? Sine x, because sine x is inside some parentheses. A lot of the times, what's inside stuff is either inside parentheses or under a square root. So we say u is sine x. So again, you can also kind of come up with a shortcut. I could tell you what dx is without writing what du over dx is. We know dx will always be du over the derivative. So if you like just going straight to du dx equals the derivative and then solving, you can do that. If you like kind of taking shortcuts, you can say, well, I know it's going to come out the same way every time. It's always going to come du dx equals derivative, so it's always going to solve by being dx equals du over the derivative. So this is just a little shortcut. It's not even that. It's not that hard to solve for dx, but anything that saves time can be helpful. So now we substitute in. We know what dx is, we know what u is. So we replace. Instead of sine, I put u to the third. Cosine does not get replaced. if cosine did not cancel, we would have a problem, and it's possible we couldn't integrate this problem by hand. If I had no cosine here and I replaced with du over cosine x, and I ended up with a u and an x that I couldn't cancel out, then we might have to say, well, this one I cannot integrate this way. But this one we do have our cosines cancel. We just now have a polynomial, so we can do anti-power rule pretty easily. So we add 1, we get u to the 4th, divide by 4, plus c. And then what do I need to do to finish this? Substitute u back in. So we get 1/4 sine x to the 4th or sine to the 4th x. If you write sine x to the 4th, you would have to write sine x back in parentheses. And if you're ever unsure if you did this correctly or not, I could always check it by taking the derivative. I can always check this by saying derivative of the outside, so bring 4 times 1/4, evaluated at the inside, times the derivative of the inside, and then derivative of a constant would be 0. So we just get 1 sine cubed x cosine x, which is what we started with originally. So you can always differentiate to make sure you're doing this correctly. So one set of integrals we have not practiced yet are exponential and logarithmic integrals. So we are going to need to make note cards for these. These are formulas we need to have memorized. Just like we had to memorize the derivative of e to the x, the derivative of a to the x, the derivative of log base ax. Okay. These are our 5 new integrals we need to have memorized. Of course, the integral of e to the x is e to the x, just like the derivative of e to the x. E to the x is e to the x, plus c though. Integral of a to the x is a to the x over ln a plus c. Integral of 1 over x, which up to this point we have not been able to integrate because that's the same as x to the negative 1, is natural log of absolute value of x plus c. That's a little bit different. Before we had natural log of x, and when we took the derivative, it was 1 over x. But because natural log, you cannot take natural logs of negative numbers, we had to include that absolute value. The integral of natural log x itself, which is x ln x minus x. All of these are plus c. And log base ax is x ln x minus x over ln a. So very similar to a to the x. Okay, so here's our last try problem. Again, it's involving a lot of different types of functions. So what do you guys think you will be on this problem? The only one I heard an actual function out of was Eliana.
What did I say? What did I say?
And now she can't remember. Okay? Normally, it's what's inside parentheses or what's under a square root. None of these are happening right now. What if we have an exponential function, though? The exponent is always considered the inside if the base is a number. Use a number. Sorry, I don't know what just happened. Oh. Okay. So, e is our number, cosine x will be our inside. So when you went through, you should get negative e to the cosine x plus c. And now for one of my favorite jokes of the year, just because it's the one I remember from high school calculus. This is my high school calculus's
high school calculus teacher's math joke. What is the integral of 1 over cabin d cabin?
Wait, why are there 2 C's?
Because
Oh, I was like,
I wasn't paying attention when I was saying. I was too excited to tell my joke.
okay,
What was the integral of 1 over x?
it's,
It's one of our new formulas.
with ln absolute value of cabin.
ln absolute value of cabin plus c. So it's a log cabin by the c. Yep. Good old high school calculus. Miss Baker. Hey, she had red hair too. I was just trying to channel Miss Baker this year. Okay, and here is your assignment. Chapter 7 is a little bit better organized than Chapter 6, so we will be doing more book assignments this chapter.
Was?